All right, welcome to the last section of Unit 5. I believe it's the last one. 2.5, uncertainty in measurements. So when measuring, you're going to get an uncertainty range, and that's what uncertainty is. It's a value that, let's say you give someone 10 and it's plus or minus 5 would be the range or the uncertainty. So let's try this. What is the range for 10 plus or minus 5? The symbol plus or minus means plus or minus. So we just do 10 minus 5 is 5, and 10 plus 5 is 15. So the range is from 5 to 15. That's all that means. And we're going to be doing that this unit, measuring the range of the uncertainty of something. So first little part here, Beatrice is a baker, and our Viet, she is measuring milk. She's using a measuring cup that is precise to 1 fluid ounce. The recipe calls for 8 fluid ounces of milk. How can you represent the uncertainty in Beatrice's measurement with a number? Hint on the side here, a rule of thumb is that the uncertainty in a single measurement is half the quantity between scale markings. Okay, that's where this comes from. So what is the uncertainty in Beatrice's measurement? The uncertainty is half times the smallest scale interval. So that'll be 0.5 fluid ounces, because 1 is her smallest. So half of 1 is 0.5. What is the tolerance interval of Beatrice's measurements? Tolerance interval is right here. Tolerance interval, the smallest range of measurements that includes the true measure. For example, the tolerance interval for a millimeter in a ruler is plus or minus 0.5. Okay, so tolerance interval of 8 fluid ounces is plus or minus the uncertainty equals 8 plus or minus our 0.5. So 8 plus 0.5, 8 minus 0.5. So we get 7.5 to 8.5. The tolerance range is from 7.5 to 8.5 fluid ounces. What is the tolerance of Beatrice's measurement? Tolerance is equal to the maximum limit minus the minimum limit. And here on the side it says tolerance, the difference between the minimum and maximum differences. So our max that we calculated was 8.5 and our min was 7.5. So that equals 1. The tolerance is 1 fluid ounce. Not too bad. So example 1. We have Wes and Jamie did the 100-meter sprint in different track meets. Which timer is less accurate? Wes's time at a high school track meet was 12.78 seconds. The race was timed by an official using manual. Oh, I don't like manual stopwatches. Jamie's time at a university track meet was 12.182 seconds. The race was timed by electronic, way better. The device was triggered by the runner at the start and the end of the race. Solution. What is the range for Wes's true time? So uncertainty is half times 0.01. So we get, type that into your calculator. That'll be 0.005 seconds. The tolerance interval means his time plus or minus 0.005. Wes's true time lies between 2.775 and 2.785. what is the range for Jamie's true time? So again, we're going to do half times 0.001 because that's what her time was up to the thousandths. So we'll get 0.0005 plus or minus 0.0005. So her time lies between 12.1815 and 12.1825. Which timer is less accurate? The stopwatch. It has more uncertainty. And that's because you can see the uncertainty lies between here to here, but for the timed stopwatch, that one is more precise because it's to a smaller decimal. And hint, use the word uncertainty, we did. Okay. Example 2, Sadie and Perry measure the voltage of different car batteries. Which reading can you be more certain about? Sadie uses an analog volt that is precise to plus or minus 0.2, and she got 12.4. Perry, digital that is precise to plus or minus 0.01, and he got a reading of 12.33. What's the range? So all we have to do is put the numbers in. So 12.4 plus or minus 0.2 is, so this one's 12.6 and this one's 12.2. So we got 12, the range is 12.2 to 12.6 for Sadie's. The range for Perry's was 12.33 and plus 0.1 is 12.34 and 12.32. So the range 12.32 to 12.34. Good. What is the percent error for each reading? So percent error is uncertainty divided by measurement. Sadie's reading is uncertainty divided by 12.4 is about 0.016 or 1.6%. Perry's, well, this one was 0.01, right? Divided by that will be 0.0008 or about 0.08%. Which reading can we be more certain on? Perry's, the digital voltmeter has a lower percent. And we can see that right here. This one's lower. Awesome. Okay, so on to the practice section of this. We have how many pages of practice here? 1, 2. Okay, well, let's do this chart. I'll start it with you guys. So we have the precision, uncertainty, tolerance, and range. And we have some measurements here on the side. So let's do the first one. It does it for us. 1.64 precision. nearest hundredth of a centimeter, or it goes to this decimal spot, right? Right there. That's where that comes from. Then they did that divided by 2, which gives us our uncertainty, and we're doing precision divided by 2 for all of them. It gives us a tolerance interval of this plus or minus 0.005, and then we get the range by adding that or subtracting that. So we get our range from there to there. So let's do, I'm going to do that one, and I'll do that one. You guys do 10.09. So nearest 16th of an inch, or 1/16. Okay. So I have to go 1/16 divided by 2 is going to equal to 1/32. So we have 2 5/16 plus or minus 1/32. That means that my range is 2, 9 32 to 2, 11/32. So you guys do the next one, and then I'll do this one. So my precision is to nearest 10th, so 0.1. That means I take 0.1 divided by 2, which will equal 0.05. And you're doing the exact same thing for the thing up here, but it'll be to that decimal spot. Then it'll be 98.5 plus or minus 0.05. And that'll give us a range of 98.45 to 98.55. Okay, awesome. Moving on. What are the percent errors for question 1? Percent error is just the uncertainty divided by the measurement. So our measurement for that was that divided by that. That was our uncertainty divided by our measurement, which is from here. Will give us a decimal 0.00304 ... It'll be about 0.3%. I can do this next one as well. 16/1184, or about, if you put that in your calculator, 1.3%. You guys can do this next one, and then I'll do this last one. My uncertainty was 0.05 divided by 98.5 equals 0.0005, or if I times it by 100, 0.05%. Good. Order the measurements in part A from least certain to most certain. I'll give you the least. 2 5/16. So that's the least one right there. Then there'll be the other 3. So you order the other 3. You can tell this answer by the percents that you'll get for each of them. The smaller the percent, the least certain to most certain it is. right? So this one had the most percent up there, the biggest percent. Then the next one would have the second biggest percent, then the least big, and then the smallest percent. Okay? Okay, so let's move on to number 3. Which tool has more uncertainty? A ruler that measures in 1/16 of an inch or a laser tool that measures thousandths of a foot? I'll just give you this one, the ruler. And the reason why is ruler uncertainty is 1 in 32. Of 1 in 12 of a foot, which gives us a value of 0.0026. The laser tool goes to uncertainty of 0.0005. So that's why this isn't as precise as this. Okay. Next page we have, I think this is the last page in our booklet. We have 3 questions. So I'll give you 6, and then we'll look at 4 here quickly. So resistors control the flow of current in circuit boards and many electronic products. What is the tolerance interval of the tolerance for each resistor? Colored bands show the ohms, the resistor, and the rated for, and this is the nominal value of the resistor. The calculated color band shows the range of possible errors in the nominal value. So silver is this, gold is that, red is that, brown is that. The nominal value is 100 ohms. The last band is silver. So uncertainty. Uncertainty of silver. That means the uncertainty of this one is 10%. So 10% of 100 is 10. Tolerance interval is 100 plus or minus 10. Max minus min is 110 minus 90, which is 20 ohms. The nominal value is 250 ohms. The last band is red. So now you figure out using the same kind of method here, except for red. And red is plus or minus 2%. So do the exact same thing we just did, but for red. So that one's U. Let's look at 5. When no tolerance is given, the machining industry uses the standard tolerance intervals in this chart. This says tolerance interval and precision. 1 decimal place plus or minus 0.2, 2 decimal places plus or minus 0.01, and etc. What is the percentage error for each measurement? Use a standard tolerance interval. All right. I'll do A. So we have, this is to the 2 decimal places. So I'm adding a measurement of plus or minus 0.01. So 0.01 over 5.35 equals 0.0018, which is how much percent? 0.18% because I times by 100. You do this one. That's to 3 decimal places. Do the exact same thing here. Okay, and then the last little bit here is, let me fit this up. I guess, yeah, that's an issue I could come across. Okay, the last rule. Number 6 here, what trades or industries might use a millimeter steel ruler or vernier caliper? How are these tools used? Don't even worry about 6. Okay, so that's the unit. Awesome. Next unit will be unit 6, so stay tuned.